We're going to do temperature dependence of a reaction rate, right? What we're going to try to do is to see whether a reaction follows Arrhenius behavior. What follows Arrhenius behavior? If you have Arrhenius behavior, then you follow the Arrhenius equation. That is, the rate constant is a function of temperature and has an exponential dependence on it. If, when we make an Arrhenius plot, which is take the log of this, right, log of K. So if you get a straight line in a plot like that, we say a reaction has, it follows Arrhenius behavior. So that's what we're going to do today. We're going to measure the rate constant as a function of temperature. Okay, so then the experimental procedure is exactly what we did before. We take a flask of dye, we take a flask of NaOH plus KCl, right? We added KCl to keep that constant ionic strength. And we're going to put them in a bath, some T bath, right? Temperature of the bath, right? And we're going to allow them to equilibrate. Then we're going to mix them together. But we have to keep, right? The rate constant is temperature dependent. So we have to keep the temperature constant because we're going to take those two flasks, we're going to mix them together thoroughly, just like we did last time. Then we're going to take out some solution and put it in a cuvette, and we have to hold that cuvette at the same temperature as the bath, right? So we get that to set the cuvette temperature in the spectrometer to the same temperature as the bath. T cuvette has to equal T bath so that the temperature is constant throughout the experiment, right? Now, okay, a couple of things about that, that bath, right, that we're going to use to keep that temperature constant. One, when you turn it on, especially like now, if you turn it on after it hasn't been used for a while, you might hear a beeping alarm. The beeping alarm is going to be because it's low on water. If you hear that beeping alarm, you just have to fill it back up. You would get me and I put some water in the back. That'll get rid of the alarm. Two, the heating element is really good. There isn't much cooling power though, okay? And this is one of the things you'll see very often with heating units and their feedback surface circuits. They heat well. In fact, they heat a little bit too well and they'll blow through the temperature you set. So I always like to set the cuvette temperature to say 0.2, 0.3 degrees below the temperature I actually want. And then when it blows past that temperature, oh, I can reset it to the temperature I actually want, because it takes it a long time to cool back down. It heats up quickly, but it cools down. If you change the temperature by 5 degrees, like we're doing today, between spots, then 0.2, 0.3 degrees is a good offset, right? If you're going to change the temperature about 20 degrees, it may blow through it by half a degree or more. And so you would appropriately set the temperature first to a little bit lower, allow it to go past that, and reset it to the temperature you actually want it to be. You got to make sure the temperature of the bath, the temperature of the cuvette are the same before you start taking data, and that they've equilibrated, right? They're still, you know, it's not still trying to feed back and change that temperature. You want them to be the same, all right? Similarly, because it takes it a long time to cool down, always, always, always at the end of the experiment, turn the temperature back down to 25. You don't have to wait for it to get back to 25 before turning it off, but reset it to 25. It always remembers the set point that it was at the last time when you turn it off, right? And so you want to reset it to 25 degrees C, because if somebody comes in and it's at 50 degrees C and they don't notice, it's going to heat that sample up, and it can take a half an hour or more for it to cool back down. So it's just rude if you leave it at high temperature. Always reset it to 25. The experiment tells us to take a constant amount of NaOH, right? We're going to put 5 mLs of NaOH. We're going to use a constant concentration of NaOH. We'll have to figure that out. All right. So we need to know the initial concentration, and we need to do the dilution, right? Because we're going to take 5 mLs of that and dilute it out to, oh, it's going to end up being 60 mLs is our total volume in the reaction flask. We always have to figure out what the initial concentration of the OH is. We're going to keep that constant throughout. And then we're going to need to take absorbance data, and then we're going to convert, right? We're going to convert absorbance into concentration data. All right, let's do all that. So we take some data, take six sets of data, for temperatures between 25 and 50 degrees C, more or less evenly spaced. So we're going to convert absorbance to concentration, right? We're going to use the orders that we determined from before, and what we should have found, right, is that it's first order in crystal violet, first order in hydroxide. That's the real kinetics of this. So it's second order overall. All right, we're going to use that. I'm going to give you a new value of A naught and C naught. So we're going to calculate a new epsilon value, right? And then we're going to use that to convert our absorbances to concentration. And then we're going to make up this plot, prepare an Arrhenius plot. ln k versus 1 over T is what we have to do with temperature, of course, in Kelvin, right? Intercept is the log of the pre-exponential factor, and the slope is related to the activation energy. All right, so let's take it to Igor. And now what are we going to do? Well, we have to load some waves, right? So general text, we're going to load our we've got 6 systematically named waves here. So let's do that. We're going to use systematic names, time 1 and A1 for the first absorbance. Then we're going to do that again for the second wave. All right, okay. Let's do that. Time _2, A _2 for the second one. We're going to load Well, what I'm going to do, I'm actually going to use the procedure window here, and you'll see why. And I'm just going to make a little holder that I'm going to call macro calcs, right? It doesn't have to actually, we're not going to run it as a macro, but all macros come to an end. And if this was a real macro, that's what we'd be doing there, right? What do we need to do? We need to convert absorbance into concentration. Absorbance is equal to, right, epsilon times path length, right, Beer's law here, right, times concentration. All right, path length is just 1 centimeter. Concentration we'll need to know. Okay, so what we needed to do was calculate epsilon from, right, an A naught value, and we're going to divide that by B times C, right? Okay, so we actually know what that was. The A naught value for this experiment, it's a new one, 0.734, right? The B value is always just 1 centimeter. Okay, so we don't really need that in this calculation, but we need it for the units to get that right. And then the concentration, oh, wait a second. We need to figure out what the concentration was, right? Concentration, right, our C0, right? We had some concentrated solution, right? And then we took 10 mLs of that, we diluted it to 100 to make the stock. And then we took 10 mLs of that and we diluted it out to 60, right? And this concentrated solution this time around, it's 4.11 times 10 to the minus 4 molar is what we had, right? Okay, so then if we, this is the calculation we need to do. If we want to do that calculation, easy way to do that calculation is take it down to the command line down here and say print, put in what you wanted for the calculation, hit enter, and oh, it tells us, right, that that is actually equal to 6.85 times 10 to the minus 6. Okay, good. So that's the number we'd have to put in here, right? 6.85 times 10 to the minus 6, right, to get epsilon. So again, we could figure out what epsilon should actually be by saying print, paste that number in, return. Oh, okay. So we get the epsilon value. 107, 153 is the value of epsilon. Let's just take a look at our data, right? What we've got is A1 versus time 1, right? Bam. But that's not the data we want, right? What we want to do is plot the log of the concentration, right? Oh, okay, so wait a second. So we need to make a new wave, right? Let's make a new wave. And it's going to be the same length as the absorbance data, right? But it's going to be the log of the concentration, not the absorbance, right, that we want. So the log of the concentration, but it's going to be the same length as A1. So why not just duplicate it? That's an easy way to make sure you get the same number of points in it, right? And I could do it, right? But instead, let me take that to the clipboard, right? And then I'm going to go up here into this procedure window and I'm going to paste that in, right? And that's how I could make the concentration wave. And then what I want to do, right, is I'll need to plot this. Oh, wait a second. All right, I need to make a plot of ln concentration versus time. So it's the same kind of plot, right? Let me get rid of this. I don't want that one. What I actually want is this one down here, right? I want the same kind of, I'll copy that command because that's the command I want. Let me put that in there, but it's not A1. It's going to be ln C1 that I'm going to plot versus time, right? But how do I make, all right, wait a second, I need to actually calculate what the log of the concentration is, right? And the log of the concentration is equal to the log of, oh wait, if I want concentration is equal to the absorbance divided by epsilon, right, times b, path length. Okay, so then I need to take the log of the absorbance, A1 in this case, and I need to divide the absorbance by epsilon. Oh, I know the value, 107, 153, right? Okay, so that will give me the convert absorbance to concentration, then I take the log of it. Okay, there we go. And I'm going to plot that versus time. Great. And then what am I going to do? Go and fit that to a line. And then the slope of that line is equal to the negative of the right back here, the slope, right? It's a first order fit. So the slope of ln C1 versus time. Let me just do, oh, in fact, I could just copy these and paste them down here, boom, into the command line, right? And hit enter. And sure enough, it actually, oh, yeah, it plots those up and it looks linear, right? And then this, if I do a fit to this line, it would give me the pseudo rate constant. The negative of the slope would be the pseudo rate constant. And then I'm going to use that to calculate Kp, and I'm going to plot the log of Kp versus, oh, wait a second, we need some other waves, right? Let's make some more waves. And they're all going to be 6 long, right? That take some data as a function of temperature. We're going to take 1 over temperature, the inverse of temperature, right? We're going to get Kp values. We're going to use those to calculate the true rate constant, and then we're going to plot ln of K versus the inverse of temperature, right? Oh, okay, so I know I need all of those, so I made those. Let's make up a new window, a new table with the temperature, Kp, K true, ln K, and I need the temperature there. Boom. And okay, let me get these down here, right? Let me move this around, Alt, and I'll hold that and move it over here. I'm going to turn those into the temperatures that we used 25, in this case, 31, 35, 42, 45, and 50. But wait a second, we can't use temperature in Celsius instead, right? We have to convert that to Kelvin, and we're going to say that the inverse temperature is just 1 over T, right? Boom, we got those numbers. We can format that nicely, make it scientific with 2 is just fine. Great. Okay, good. Now we want to calculate Kp. Kp is negative of the slope of this, right? Oh, okay, so what we need to do is we need to do a data analysis. Curve fitting. We're going to do a line of the log of concentration 1 versus time 1. We're going to fit that to a line. All the data, 95% confidence limit 1, put up there. Boom, done. Oh, there we go. Hey, we got it. All right. And then, right, let me pull this out here so we can see it. Kp is just equal to minus the slope. Oh, wait a second, but the slope, right? Oh, here we've got, there's the intercept, right? And the slope, there's the slope right there. Oh, it's calculated for us. We don't need that. In fact, the slope has been put into a wave that's called W cof, right? And it's not the first element, it's the second element. The first element would be element 0, the second element is element 1. Oh, wait a second. So the Kp, the first element in the Kp wave is Kp 0, and it is equal to minus W underscore cof 1, right? That's this value here. It's the element 1, point number 1 out of the cof wave was equal to the slope, all right? Yeah, good. All right, wait a second. Now, why have I typed all this in here? Why? Because, right, if I just take this, right, I'm going to do this, I'm going to have to do this 6 times, right? So now I can just copy and paste, right? I could do this again. Here, watch this. Right, I've already got the wave. I don't need to create that wave again. But if I paste those commands into the command window, boom, it has now made the graph for me. It has done the fit. It's calculated the Kp value and put it right in here. Oh, neat, right? And you can, how do I get the fit in there? Oh, wait a second. It's easy to do. Curve fitting, right? I need a line fitted to LNC1 versus time 1, all the outputs and everything. But what I should have done was go to the clipboard, right? Pop in the values here. Just paste that in. Okay, so now I can take these. Let me just do it one more time. Let me get rid of that graph, right? Don't want to save that one. I'm going to make it again. See, easy as that. You paste into the command window, hit enter. There it is. I'm going to move it over here so that I can save all of these. You'll see all of them. Boom, it's calculated the Kp value. And now you can see that there's the fit wave. Oh, if I actually make the one a different color, then sure enough, you can see there's a fit wave and the data wave, pretty good fit to a line, right? Alrighty, good. Now, what do I have to do? I have to do this for all the other data sets. Wait a second. It's exactly the same procedure, but I need to change the names. And if I use systematic names, I can just do this. Now I'm going to do it for the second data set, right? Second data set's going to be A2. I'm going to turn that into LNC2. All right. It's the same epsilon, but I just need to change the name of the wave and I get exactly the same calculation done, right? So let's change those to 2, right? 2, 2, and we need to move this up 1. It's going to be it's going to be a new fit, right? And here we go. We'll copy that. We'll paste it down here into the command line, hit, and there it is. I now have my second graph and a second value of Kp, right? Hey, if it works for Kp once, it'll work again. So let's now do it for 3. Notice that I've got it all here. If I made an error, I can look back and say, oh, wait a second, I have to redo that one. Very easy to redo the calculation now because it's all preserved here in the procedure window. I see exactly what's going on. All right. And so I can go back, I can check it, I can use it again later if I was ever going to do this analysis again. Right, it's all available for me. All right, so I stick it into the command window, bam, and we've got all 6 values of Kp, right? And then if I want K, the true rate constant, true is equal to K, equal to Kp, right? What did it tell us here? Kp, it's actually equal to, right, from the log there, we need to take Kp and divide by the OH concentration, right? Divide by the OH concentration. So OH minus, right? That's what we need to do. Oh, okay, so wait a second. What was the OH concentration? The OH concentration, right? The OH concentration is equal to the initial OH concentration, which is 0.09972 molar. And then we took 5 mLs of that and we diluted it to 60 mLs, right? So that was the OH concentration, which again, if we want to know the value, go down to the command line, print, type in there, boom. All right, it's equal to 8.31 times 10 to the minus 3 molar is the OH concentration. And to get K true, right, K true is equal to Kp, right? We can do it for the whole wave all at once, divided by 8.31 times 10 to the minus 3, and boom, we have the K true values. All right, then we'll want the lnk values. Lnk is just equal to ln of K true. Bam, we got all of those as well. And then to make the Arrhenius plot, we need a new graph of lnk, all right, lnk versus the inverse temperature. Bam, there we go. Looks like we got an Arrhenius plot. We want to make data points look like points, so we're going to make them markers, and we're going to pick a useful marker. I hate that plus sign. Boom, there you go. The Arrhenius analysis is to take, right, a line, fit it to lnk versus 1 over t, right? Make sure you have the 95% and the text box, boom, make it look like a real graph. There's your slope. Minus r times that slope will give you the activation energy. R times this uncertainty will give you the 95% confidence limit in the activation energy. There's the intercept. It's in the units of per molar per second because it's a second order rate constant, right? And Bob's your uncle, all right? So all of that taken care of right there. Remember, you've got now this procedure window that has all of the numbers you need, the new A naught value, the new C naught value, the concentration of the OH originally, right? You need all of those values in order to figure out whether this system follows Arrhenius behavior. Yeah, we got a straight line there, right? And what was going on. Remember that it's first order in crystal violet, first order in hydroxide, so it's second order overall.